Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today, we are going to discuss how to find the area using the limit approximation method. So if you have covered the Riemann sums, you learned about, the trapezoidal method or Simpson's rule or any of these things. You learned that when you use you get an approximate area under the curve. That's the introduction to integration, of course. But the limit approximation method gives you the exact value of an area under a curve. So if I have a graph f of x, okay, so let's assume we have a graph here, something like that. I know f of x, it's given to me. And I want to find the area under it between points A and B. So instead of dividing that into 3 or 4 or even 10 strips, I'm going to divide it into infinite parts or infinite rectangles. Each rectangle will have a height, which is f of whatever value of x is between A and B, and a width of delta x, or in fact dx, because the limit as delta x approaches 0 we call it dx. So that should give me the exact area under the graph, but we have to write it in a way. So what we are going to say is that limit approximation method says that the area under the curve is the limit, and that's why you learn limits, n approaches infinity of a sum that goes from I equals 1 to n that approaches infinity of f of something, which is the height, times delta x, right? Delta x. What is this thing? How do I write it in terms of A and B? Well, the first one is A, and its base is delta x. But what is delta x? It's very easy. The total base of this shape is b minus a, right? B minus a. And I'm dividing it into infinite numbers that are called n, and n would approach infinity. So each one of these extremely small, infinitesimally small bases are b minus a over n. But how do I find, say, the height, which is f of this value? First, I get this value, write it here, and take the f of that. But how do I find, suppose this is after 15 delta x's. It would be, what would be the value here if I drew 15 rectangles with width delta x? Yes, it would be a, which is this, plus b minus a over n, which is delta x, times 15. And then the one next to it would be times 16, times 17. Oh, wait a second. But I have these called i's. So it's a plus b minus a over n times I. And delta x is b minus a over n. And this is the equation that I don't want you to memorize. Just understand what we are doing and you would remember it. Because I've seen people try to memorize that. And is it a minus b or b minus a? Do I multiply inside by r or outside? No, don't do that. You already learned how to find delta x from the other rules. B minus A over N. If I divide it 3 times, I divide by 3. If these are 10 rectangles, I divide by 10. If they are n, where n approaches infinity, I divide by n. And then I start at A and keep adding delta x, another delta x. So delta x times 1, times 2, times 3, times I. And you take the function of that. We'll see how it's a little tedious. I give you that, but it's not hard. Let's say I have a parabola and I want to find the area under y equals 4 minus x squared, and x is greater than or equal to -2, less than or equal to 2. So you don't need to plot it. You really don't, but it's easy. First of all, it has its vertex is the y-axis because x is squared, not x minus 1 or plus 4 or anything. It's opening downwards because of the negative sign, and it looks something like that. Not down to scale, but this is -2 and 0, this is 2 and 0, and this is 0 and 4. And we want this area. Let me tell you something. What did I want to say? Yeah, if you checked my engineering statics course, in one of the lectures, I was showing you how to find the area of like second degree or third degree parabola or nth degree, but I gave you the area here, say this area. And I told you this, if it's a second degree, this area is 1/3 base times height. And of course, this one is the same. So that is 2/3 base times height. And this is 2/3 base times height. Well, this is the base, that's the height. And this is 1/3 base times height. So really, it's 2/3 2 times 4 plus 2/3 2 times 4. So you can say it's 2/3 base times height. So 16 32/3. So that should be the area. We can check. We can check first and say go to math. And then I think 9 is the finite integral from -2 to +2 of 4 minus x squared dx. 10.666, which is 32/3, correct. So I really don't need integration. I don't need this, but it's good to know the final answer. So if you get something wrong, you know where you messed up. Okay, so first of all, A here is -2, B is 2. So B minus A over N is 4 over N, right? 2 minus -2 over N. Okay, so now I can rewrite this as A equals the limit as N approaches infinity is sum of I going from 1 to N of f of 2 plus 4I over N times 4 over N. There is no I outside, of course. It's B minus X, delta X. That's the height, that's the base. But how do I find this? Well, it's the limit as N approaches infinity, summation I going from 1 to N of Now, when I say f of something, it means in your equation, every time you see x, you replace it with what's between the parentheses. So I have 4 minus, and then I have x squared. So instead of x squared, I'm going to write 2 plus 4I over n quantity squared. And this is multiplied by 4 over n. Nice? So far, so good? Equals the limit as n approaches infinity, summation I going from 1 to n of 4 minus, and then between parentheses, I'm going to square that. Square of the first, twice the first times the second, square of the second, and then I simplify between the parentheses. So 4 minus 4 cancel, right? Just a second. Yeah, I have a minus here. Okay, so I have do I have the impression that no, it's correct. Okay. No, something doesn't add up. Four minus x squared. Yeah, a is negative 2. Of course, something couldn't be all negatives. Okay, this is negative 2. So that is a negative 16, and that's a positive. I said it doesn't make any sense to me. Okay, but still, when I square the negative 2, I get positive 4, so they cancel. And then I would say, I'm really sorry, guys. Limit as n approaches infinity, summation I going from 1 to n. I have negative times negative is positive. 16 times 4 is 64I over n square. Negative times positive is negative. 64 again, I square over n cubed, because the n is multiplied. And here, really, where we find ourselves with I and I square, and sometimes we can have a constant term. Here we didn't, because the 4 and the 4 canceled, but suppose this wasn't the 4, I would have another number. So here we have to find out, if I have a constant c, what is the summation I going from 1 to n of c? Meaning I'm counting c n times. That's nc, right? Or the summation of I going from 1 to n of 1 is n, right? What is the summation of I going from 1 to n of I? Meaning 1 plus 2 plus 3 up to n, whatever n is. Yes, that's the sequence. In arithmetic sequence, you can find its series by saying the last term, which is n, times n plus 1 divided by 2. That's how, in fact, in the test, they give you these equations, but I will show you how you can find them easily. N times n plus 1 over 2. But I'm going to write it as n squared over 2 plus n over 2, and you will see why later. Then you get the summation of I going from 1 to n of I squared. I'm going to give you the answer right away, not in this form or the form you get at school. No, I'm going to show you a much easier way. N cubed over 3 plus n squared over 2 plus n over 6. I will explain these to you. In fact, you will see most of the explanation without me talking. I cubed, I get n to the 4 over 4 plus n cubed over 2 plus n squared over 4. In fact, if I want to give you another one, but you will never need it, they will never give you a problem where you have to sum I to the 4th, but this would be n to the 5 over 5. Oh, you expected that, right? It's as if I'm integrating with respect to n. The value c, which is constant, you get cn. If I want to integrate n, I get n squared over 2. If I want to integrate n squared, I get n cubed over 3, n cubed, n 4 over 4, n 4, n 5 over 5, or I to the 4. The second term, of course, it decreases 1. So the square becomes linear, the cube becomes square, then linear, cube, and so on and so forth. The second always stays over 2. Excuse me. But how about this new term that shows up? Well, you can think of it here as what makes the sum of the coefficients 1. You say, why 1? Well, basically because if you say, I'm just going to add I squared from I equals 1 to 1, just make I equals 1. So the answer would be 1. Meaning I took one term, so the sum has to be 1. 1/3 and 1/2 is 5/6. So what makes it 1? Another 1/6. Here, a quarter and a quarter is a half, and a half is 1. A half and a half is 1. 1. Here, but basically, once you get the first term here, you don't need to subtract, and so you don't have to add and subtract from 1. Going from here to here, you multiply by 3 over 2. Why? Because here it's square, here is cube. That's the easiest way to remember. 3 over 6 is 1/2, over 2 is a quarter. So what do you think I'm going to multiply here? 4 over 3. So that becomes n cubed over 3. But then, unfortunately, every time the number of terms repeat twice, like here there were 3 terms, here there were 3 terms, then the next time there would be 4 terms, and then 4 terms, and then 5 terms, and 5 terms. Don't ask why. Just try to go online and check Bernoulli numbers, because they will keep popping up here. We don't need that, but if you want to know, then use this the sum that the coefficients equals 1. 1/5 plus 1/2 plus 1/3 equals what? The LCM is 30. Divided by 5 is 6. Divided by 2 is 15. Divided by 3 is 10. They add up to 21. 31 over 30. So I have to subtract n squared over 30. Then as I go down, I will multiply this by 5 by 5 over 4. And then this would be multiplied by 5 over 2 instead of 3 over 2, because it appeared in here the power was 3. So I go by multiplying 3 over 2, 4 over 3, and so on and so forth. This one is a 5. So the next one would be times 5 over 2. So n cubed over 12. Anyway, that's not our issue. I'm sorry I made it so hard on you. But, as I said, these will be given to you, but you can get them or you can remember them very easily. Now let's go back with this information with us, because what I have here are 2 summations. I can divide that into 2 summations, or I can just do it once and for all. Let's play it safe so I don't confuse you, because I think I made it hard here. Again, you don't have to worry about that in a test. or even in your book, they will give you these equations, maybe in a more compact form. So they tell you, for example, this is, usually they say it's n squared times n plus 1 over 2 square, or some other form, but all of them are the same. So let's play it safe and say it's the limit as n approaches infinity of summation I going from 1 to n of 64I over n squared minus the summation I going from 1 to n of 64I squared over n cubed. Okay, just to be easy. The limit as n approaches infinity of, well, the summation of I is n times n plus 1 over 2. Or, as I said, n squared, so you can write it as 64 over n squared. And then the summation of I, as I told you, is n squared over 2 plus n over 2. Minus 64 over n cubed, and the summation of I squared is n cubed over 3 plus n squared over 2 plus n over 6. Now we take the limit. If I divide n by n cubed, when n cubed goes to infinity, then this will be 0, this will be 0. Same thing, if I divide by n squared, this would be 0. So that's the easy part in the problem. Well, the limit of n squared over n squared is 1, and you get 64 over 2, which is 32, minus n cubed over n cubed is 1, 64 over 3, equals, if I take a common denominator of 3, I get 96 minus 64 over 3 equals 32 over 3 equals 10 and 2/3. Which we already did here, right? And we did it 32 over 3, here it is, and we did it with the calculator. So basically we found the limit approximation of an area, and we got the exact answer. So we started with, trapezoidal method. We calculated from the left and from the right. We got a lower limit, upper limit. We said we can average. We used the, trapezoidal method. Some of you may have used the Simpson's rule. And all of these were approximations. But when you take the limit as n approaches infinity, you get the exact integral, exact value, really. And if you know how to integrate, it's much easier, right? You can say 4x minus x cubed over 3 and substitute from -2 to 2, +2. But this to show you that we really, when we used to tell you that if I make delta x very small, then this can become a rectangle. And many of you would say, isn't there like some kind of curvature? So how do I consider that a rectangle? But this proves that really, if you make it so small, very small, they are actually rectangles. And you get the exact answer, not an approximation anymore. I hope you like this lecture or this session. And again, if you have any questions, please leave them in the comment section, and I will do my best to come back to you as soon as I can. Thank you very much, and hope to see you soon.